Hello everyone, welcome back to the third talk of this afternoon session. The talk will be given by Professor Paul Linson from Aarhus University. His title is The Orbital Method and the Analysis of Automorphic Forms. So let's welcome.
All right. All right, thank you so much, Yangshang, for the introduction, and I'm very glad to be here to talk about this work that was recognized yesterday in this paper with Akshay Venkatesh called The Orbit Method and Analysis of Automorphic Forms. So it's a paper that came out in, I guess, 2018 on the archive, and it was published 3 years after that, so it's been a few more years since then, and it's led to some more work in the intervening years, but it tells a complete story on its own. So I thought I would focus on this occasion on that story, and then maybe at the very end, I'll just give a little hint about what's come after, if there's time. So we're going to present, since this is probably a pretty broad audience, we're going to present the talk kind of starting with the orbit method and saying a bit what that is classically and how it's imagined in our work. And then we'll go on later in the talk to the applications, which will involve automorphic forms and L functions. So to get started, so here's just a little introduction. So the orbit method in a nutshell, which goes back to the mid-20th century, you can think of as a heuristic for understanding representations of a Lie group in terms of its coadjoint orbits. So a coadjoint orbit, as depicted here, is an orbit for the action of the group on its dual Lie algebra. I'll give a couple examples in a second to make this completely transparent. And so the heuristic is based on what we'll call an approximate bijection between, on the one hand, the fundamental quantities in representation theory, so the irreducible representations of the group that I've called Ir of G, and on the other hand, the coadjoint orbits. So when such a bijection, insofar as it's defined, exists, we'll write O pi for the orbit attached to a representation pi. And of course, this should not just be some haphazard bijection. It should be something that behaves well with respect to the natural operations you'd like to perform on objects on either side of the bijection. So for instance, things that one might want to do with a representation include tensoring representations, inducing them, restricting them from one group to another, computing their characters, that sort of thing. So these kinds of operations should be naturally reflected in terms of typically simpler operations on coadjoint orbits, and hence might give some way to understand those more complicated operations on representations. And so I say heuristic here, but of course, this is kind of just the starting point, the way it was initially introduced. It comes with a number of rigorous theorems that implement this heuristic in various cases. But in all cases, it can be viewed as kind of a guiding heuristic that motivates how to think about these objects. So before I give an example, I want to give just one very, very concrete instance of what it means for this bijection to be compatible with the natural operations. So one natural operation is you might want to take the trace of a representation. So this is packaged in a function on the group called the character of a representation that I've denoted by chi pi here, which takes an argument as input and spits out the trace of its action on whatever vector space the representation is defined on. So the Kirillov formula, which was proved, first in some cases by Kirillov for compact groups, nilpotent groups, and then in various other generalities by other authors, gives a formula for this character on small group elements. So in particular on group elements that you can write as the exponential of a Lie algebra element that I've called X. And it says that up to some Jacobian factor that you can ignore kind of at first glance, this character is given in a natural way in terms of the coadjoint orbit O pi. So in particular, you can think of this formula as defining what the coadjoint orbit should be. It's pinned down by this identity. And so what does the formula say? It says, well, there's a natural measure you can attach to the coadjoint orbit, such that if you take the Fourier transform of that measure and evaluate that at a Lie algebra element, that'll spit out the character of the representation at the exponential of that. So just to give another simple example of what this specializes to, if you take x to be 0, so that the left-hand side is the character of the identity transformation, so that's just the trace of the identity operator, which becomes the dimension of the representation. Whereas on the right-hand side, if you evaluate this Jacobian factor, it's normalized to be 1. And this integral has a constant integrand. So what comes out is just the volume of the orbit. So that's one special case. So now I'll give a couple of representative examples of what this heuristic looks like. But before that, are there any questions just on what we have said so far? This is just the normalization of how it's defined. Yeah. So yeah. I didn't hear the question, but okay. Yeah. Cool. So okay, one example is you take the group SO3, where its Lie algebra is now, you can think of as R3, corresponding to the 3 axes that you can rotate around. The dual of R3 is also, you can think of as R3. And the action, I said that there's an action, an adjoint action, and a coadjoint action of the group on these, and it's just given by the usual rotation, the standard action of orthogonal symmetries on the space they act on. So in particular, the coadjoint orbits are just the usual orbits of the rotation group acting on R3. So there's one orbit, you can barely see it right there, it's just the origin. And then every other orbit will be a sphere of some positive radius. So I've depicted a few of them here. So you have some continuum of orbits indexed by, if you'd like, the non-negative real numbers, starting at 0 and then kind of becoming bigger as the radius increases. Now, on the other hand, if you studied representation theory of say, SO3, or if you studied quantum mechanics, if you're coming from a physics background, you might know that the irreducible representations of SO3 are classified by a numerical invariant called the highest weight, which is a non-negative integer that I've denoted t, that indexes the representation and completely determines it. And so it turns out that the formula on the previous slide describing the character of the representation holds if you take the orbit attached to the representation of highest weight t to be a sphere of radius 1/2 more than t. So this is, if you'd like, just a kind of repackaging of the standard character formula for the sphere in the form of Harishchandra and Kirillov. But it's suggestive of kind of a geometric way to think of these characters that extends more generally, so in particular to any compact group and beyond. So to give another example, here are some pictures for the group. If you'd like PGL2R, or if you'd prefer to think of it in terms of orthogonal symmetries, SO12. And this example is particularly relevant. I don't know if anyone here studies classical modular forms analytically, but these pictures are highly relevant for that theory. So again, there are now two main classes of coadjoint orbits. They're all hyperboloids that either come in a one-sheeted variety, which I've indexed by a parameter r, or in a two-sheeted variety that I've indexed by a parameter k. So here you get these ones, and here you get those ones that split up into 2 halves. And on the other hand, if you've studied the representation theory of this group, you might know that the representations kind of naturally divide into 2 classes. There are the principal series representations that are also labeled by primarily a real parameter r. And then there are the discrete series representations that are likewise indexed by a integral parameter k. And with this labeling, there's a very natural way to describe the characters of these representations in terms of the corresponding coadjoint orbits. So you take the positive one-sheeted hyperboloid for the principal series, and you take the negative two-sheeted hyperboloids for the discrete series, shifting the parameter k by 1/2. So in both these examples, you'll notice that, up to the kind of minor if you'd like, ambiguity that, okay, not every non-negative real number arises as 1/2 less than a positive integer. And okay, I haven't mentioned this parameter epsilon, which is either plus or minus 1, so that's just kind of a sign. Let's not worry about signs for now. So up to these kind of, slight imprecisions, this actually does define more or less a bijection between orbits and representations. So it's not quite exact. It's, a bit less precise than that. But in particular, if you're doing analytic number theory, where you're typically used to a bit of imprecision anyway, maybe you're averaging over automorphic forms with parameters in some big window, so you don't really care if the window is kind of defined on every integer, you more or less care about how it behaves on small intervals in the real numbers, then this kind of ambiguity is particularly unimportant, and you can really think of this as kind of a working bijection. So hopefully these two examples illustrate that to some extent. Okay, any questions so far? I mean, maybe one thing I'll mention, if you're someone who's studied classical modular forms or representation theory, but you haven't seen it from this perspective, one kind of nice thing you can read off from a picture like this is, for instance, the weight structure on the holomorphic discrete series representations. So you might know that a classical modular form, it has these Shimura-lifts of weights, well, first k, and then k plus 2, k plus 4, and also it has some anti-holomorphic ones with weights negative k minus 2, negative k minus 4. And so you can kind of see those as the vertical extent of the two-sheeted hyperboloid that appears in that picture. So the fact that you have weights kind of only from k and up or from minus k and down for the holomorphic things, whereas you can have any allowable weight for a Moss form, if you're familiar with these things, you can see right away from that picture. So that's just one example of how these pictures can kind of be suggestive for how to understand possibly familiar phenomena from the theory of modular forms. Okay, and if there are no questions on this kind of primer on the orbit method, then I want to go to the next part of the talk, which is about a little bit on microlocal analysis, particularly in the manner that we imagine it in our paper and then apply it to the theory of automorphic forms and L functions. But okay, again, we have a broad audience here, so we should say a little bit about what microlocal analysis means in a completely general setting. So, or perhaps classically is a better way to say it. So you can think of it as starting with a function, maybe on Rn. So maybe this is the case of R1. So a function could, for example, be an audio file describing my talk as I'm saying it right now, or maybe your favorite song, or whatever you'd like. So let's go with the song example. Maybe you don't want to think of the song just as a bunch of random frequencies appearing on a file on your disk. You want to think of it in terms of like a musical staff that you could then take home and play on a piano or something like that. So microlocal analysis is basically like a mathematical way to systematize the idea that you can think of general functions in terms of something like a musical staff describing, okay, for a particular time interval, what notes are being played in the audio file, for example. So, so mathematically, you'd say, okay, let's look at a particular range of a function where it has some support, and let's take a Fourier transform just locally there and think about which frequencies show up primarily. That's kind of the general yoga of microlocal analysis. And okay, at a slightly more technical level, and you can kind of zone out now, I'm just trying to give a little bit more technical details about the paper for the purpose of this conference. The way this is actually implemented in practice is you take a function, or more precisely a symbol, which just means a function satisfying some conditions, defined on, okay, in general, you take the cotangent bundle of your manifold, but here you can just think of that as a function defined on the staff. So for a one-dimensional manifold, the staff will have 2 dimensions. And so it's a function that takes as input not just a position, but also a frequency that describes what note should be played. And you attach to any such function an operator that acts on L2 of them, which you should think of as the space of audio files. And what that function will do is, if you have it act on a vector that is localized at some position, so here at some time, and some frequency, so here some pitch, it should multiply that by the value of the symbol at the point describing the localization, and that's it. So you can think of it as kind of, for instance, if your function here is a characteristic function of just one region in the staff, then what that does is it zeroes out all of the notes except for the notes appearing in that region. So if you'd like to hear just the high notes in your song, you would apply op of A, where A is the characteristic function of a rectangle that contains all of those high notes. Okay, so there's a philosophically kind of obvious analog of this picture that applies not for L2 of a manifold, but instead for a representation of a Lie group. So again, we'll have a Lie group G and a representation pi, and we'll think of microlocal analysis as a way of understanding general vectors in our representation. So here are things that I've called V. In terms of pieces that are localized in a suitable sense, so you should think of the pieces that are localized as being kind of analogs of individual notes in this musical staff. And the analog of the musical staff, or if you'd like, the analog of the cotangent bundle, will be the coadjuvant orbit for the representation. So in the language of quantization, you think of L2 of M as a quantization of the cotangent bundle of the manifold, with the cotangent bundle being the underlying classical phase space. And in kind of the same way, you can think of the coadjuvant orbit as a phase space that underlies the representation, with points in this orbit indexing vectors in the representation that behave very simply, kind of in the same way that individual musical notes can be understood more simply than general audio files. So here's a picture just kind of indicating how to think about this for the example of SO3, where, as you can see here, we take our coadjuvant orbit, and we'll think of the following kind of heuristic. We'll take the coadjuvant orbit, we'll break it up into pieces that I'll call p tau. So a typical triangle in this picture you should think of as an example of p tau. So each of these will be taken to be of volume 1 and concentrated near some particular element tau in the orbit. So I think you take some kind of well-spaced collection of points in this soccer ball, if you'd like, and you draw little triangles around each of them of volume roughly 1. And so heuristically, the idea is, if you like, the idea is to categorify this identity relating the dimension of a representation to the volume of the coadjuvant orbit by saying we can do a bit better than that. We can at least heuristically identify a partition of the orbit into parts of volume 1 with a basis for the representation. So of course, taking a volume up here and dimension down here will recover the earlier identity. Where the vectors v tau here should somehow be described by the corresponding partition element. So for each triangle here, we get a vector down here, and somehow all of the triangles will combine together to give a picture of the entire representation or the entire sphere. And so again, in this metaphor to audiophiles, you think of pi as kind of a general audiophile. Each v tau is like an individual musical note that appears at somewhere on the staff. And this partition here into triangles is like taking the staff and partitioning it into positions where you allow a musical note to occupy. So I hope the analogy is clear and that there isn't too much notation here. So we're going to refer back to this heuristic often. We'll kind of often have in mind that we take some partition of our coadjuvant orbit. Maybe we'll vary the precise shape of the triangles depending upon what we are trying to do. And we'll have some way of going from that partition to some collection of vectors v tau that we'll sometimes call localized vectors or microlocalized, or in the physics literature, they're sometimes called coherent states. And these should behave in some sense very simply and be described by a triangle in a picture like this. So yeah, a bit more precisely, just kind of like in the classical theory, we can implement this heuristic using something like the theory of pseudodifferential operators, where we take a function, now defined if you like on the entire coadjoint representation, and we attach to such functions operators on our given representation. And these, for example, should have the property that if you take the characteristic function of some nice set, it should act on the individual localized vectors either by reproducing them or zeroing them out according as the parameter lies in the set or not. So this is kind of like the example I gave earlier of zeroing out all of the low frequency notes in a musical piece by taking E to be a high pass filter. And in particular, if you sum this over all tau in some nice partition, you see that the trace of this operator should be something like the integral of the symbol that you use to define it over the coadjuvant orbit. And so this is an association that one can just easily write down a definition for. So if you're given a function on the dual Lie algebra, you basically take a Fourier transform, truncate it maybe, and then have it act on the representation, and it turns out that this will satisfy properties something like this. So it would get very technical to say exactly in which sense these properties hold, and a good part of our paper is devoted to making that very precise. So what we have to say is, what do we mean by symbols? And the precise definition will kind of vary depending on what we're trying to do exactly. What do we mean by approximation here? But if you'd like, a good bit of our paper is devoted to introducing machinery so that you can take pictures, like in the previous slide, use them to produce proofs, and then at the end of the day, feed those proofs into this machinery to make them rigorous. So to give just a little bit of flavor for what that looks like, I mean, if you're familiar with pseudo-differential operators classically, you'll know that kind of the main technical tool that you need for manipulating them is what's called an operator calculus, that in particular gives you ways to take two such operators and compose them and understand the composition as another similar operator that should behave kind of, to first order at least, like the product of the two symbols you used to define the operators. I mean, if these operators were literally multiplication operators, then this would be an exact identity just involving the first term. It's not quite, so there's a little correction term, but we can keep track of that correction term and then make proofs out of that. And we can control the other things that you'd expect, like operator norm bounds and trace norm bounds on these things. So, okay, so this has been kind of just a general overview on the orbit method and microlocal analysis, and one way that it can be kind of reimagined in the style of classical pseudo-differential operators on a manifold, but transplanted to the setting of a representation of a Lie group. Now you might naturally ask at this point, like, okay, what can you do with this? What's the point? So I'll give a little example right now, and we'll come back to other examples later, but I want to give one example that just involves one group, because the other examples will typically involve two groups, so they're a bit more complicated. So one thing, and again, this will probably be a more convincing example if you're familiar with a classical construction called the microlocal lift that showed up in particular, well certainly in classical pseudo-differential analysis on manifolds, but also in the work of Zeldich and company proving quantum ergodicity for Moss forms, and the work of Lindenstrass and company on proving QUE, quantum unique ergodicity. So kind of a central construction in that whole story was something called the microlocal lift, which was, if you like, a limit measure that you get on certain quotients of Lie groups G. So the quotient we'll call brackets G. It'll be G modulo some discrete subgroup gamma. So certain limit measures had additional invariance, but maybe the ways that this invariance was established was a bit ad hoc and case by case, and also a bit, I think to many people working in automorphic forms, maybe a bit mysterious. So you could look at the paper of Silberman and Venkatesh, for example, and see the kind of argument they give. Whereas we can give a rather transparent construction of microlocal lifts and their invariance properties using this formalism. So now let me walk you through this slide and say what I mean by that. We'll assume given a sequence of irreducible subrepresentations occurring in L2 of this homogeneous space that I'll call pi j. And we'll also assume given a sequence of parameters, tau j, inside the associated coadjuvant orbits that tend to infinity. So you can have in mind the picture of a sequence of spheres for SO3, and maybe just take the north pole on each sphere. So that'll be a sequence that tends off to infinity. So you get from that a sequence of probability measures on your homogeneous space by taking one of the vectors that is localized at the parameter tau. So coming back to this heuristic partition, again, we had these triangles which were supposed to match up with the vectors. And we didn't make that quite precise, but if you do, you can get something like a vector. You can take its magnitude squared. It'll be L2 normalized, so it'll define a probability measure on that quotient. And so an observation that is not too hard to prove, depending upon how you make things precise, is that if you're only interested in the weak limit behavior of this sequence of measures, so what that means is, so weak topology means the topology defined by integrating against fixed continuous test functions. So if you have a fixed continuous test function, it's not changing at all. What that means is that these probability measures, you kind of can't tell them apart if, after blurring them out a little bit, they look very similar. So the observation here is that the weak limit behavior, meaning the behavior that you see after blurring out a kind of arbitrarily small but fixed amount, only depends upon the normalized limit of these points tau j. So you could have chosen any kind of nearby tau j's, and as long as you didn't destroy what this limit was, you wouldn't affect the weak limit behavior. So it's some kind of continuity phenomenon. I mean, the reason for calling it microlocal irreducibility comes from, I mean, there's a way you can view this as a generalization of the classical Schur's lemma. But okay, taking that for granted, and I mean, it just comes from the fact, really, that if you have two of these points that have the same behavior, so I think 2 points on the sphere that have very close angular distance, you can find a rotation moving one to the other. And that rotation will be a very small rotation. And the smallness of the rotation translates to very close weak limit behavior, because weak limit, again, means testing against continuous functions, and continuous functions don't change very much if you only move them a little bit. So if we take that for granted, we get a kind of very trivial proof that any weak limit is invariant by the centralizer of the limit parameter. So in the example of SO3, the centralizer would just be a rotation about some axis. And you know, the argument would be, oh, okay, we'll take something in the centralizer, apply it to that sequence. Maybe it moves the sequence just a little bit, because there will be a little bit of error in taking the limit, but it'll have the same limit, because taking limits here is equivariant for the action of the group. So you get a fairly simple way to understand that. And moreover, we'll come back to this point, because this actually is an ingredient in the proof of remain theorem. This fact that when you take a sequence of probability measures attached to localized vectors, you get invariance under the centralizer of the limit parameter. Now, I wanted to make an aside on the construction of, oh, I guess I lost that slide, too bad. I was going to give an electronic detour and explain the technology that actually went into projecting the slides, but okay, I guess I lost that one. But does anyone have questions on this one with the limit parameters or whatever? Yeah. Sorry, what's your question? Does a limit need to exist? No, I mean, have it alternate between two random points or something. But I mean, these will lie in the sphere, so if you'd like, you can always pass to a subsequence where it exists. Or, yeah, okay, that's good enough. All right, so I think that's all that I wanted to say about orbit method and microlocal analysis for one group. But as we'll come back to, when you're doing automorphic forms and L functions, there are typically two groups that are in the picture. So let's talk a little bit about restriction problems. Starting with something that, okay, if you've studied representation theory, you've probably seen the Weil restriction formula, which has the following shape. If you take an irreducible representation of a unitary group, say un plus 1, and you restrict that representation to the next smallest unitary group, un, it decomposes it in a completely explicit way in terms of irreducibles of the smaller unitary group. So there's an interlacing condition that the parameters need to satisfy. But the key feature is that each of these representations appears just once. So you have a well-defined way of taking any representation of the smaller unitary group and taking a vector in a representation of the bigger unitary group and projecting that vector onto that representation of the smaller group. And in particular, this gives a way to compute norms of vectors in representations of the bigger group. You can compute them as the sums of the norms of all of their projections. Okay. So there's a slightly more general setting in which one can do this kind of thing. So it's the setting of strong Gelfand pairs, which include, in particular, GLN plus 1 and GLN, and then similarly for the unitary and orthogonal groups, and you can also work over the complex numbers. These are kind of most of the examples. And so there you have a very similar picture, but okay, maybe it's not a direct sum, it's instead some kind of direct integral, because the parameters for these representations will live in continuous families. Where it again says that you can understand sizes of norms of vectors in terms of integrals of norms of their projections. So one reason that one might be interested in studying the norms of these projections is that these projection norms are essentially the special functions that appear classically in integral representations of L functions. So we'll come back to that. But for now, just take it as an axiom that classically, analytic number theorists have been very interested in understanding the sizes of these norms, but often in language that doesn't refer to even to representations. So it might just be a very, very complicated integral of Bessel functions involving 20 parameters that after 20 pages of stationary phase analysis, you can show is small or that you show as a main term. And so generally the analysis of these sorts of things in the settings of interest that we'll come back to a bit later had kind of run out of steam around when n was 2, so the bigger group was GL3, and at that point it became a bit too difficult for the best of us to figure out these things by hand. So one of the things we do in our paper is we give a very robust way to understand these projection norms and to produce vectors that allow us to have these projection norms be more or less whatever we want them to be. So there's kind of a forward and an inverse direction, softly and in some generality. So the idea comes from the orbit method, which, like I said at the beginning, it suggests that if you want to understand natural operations on representations, those should correspond to natural operations on orbits. So if you take an orbit for the bigger group, G, and you want to, and a corresponding representation, pi, it suggests that if you want to understand how that representation restricts to the subgroup H and then decomposes into irreducibles, this should have something to do with disintegrating its orbit under the projection map that you get on the dual Lie algebras induced by the inclusion of the smaller group into the bigger group. So I've drawn here just a couple pictures indicating how this should roughly look. And this is kind of an old story that has been used in the algebraic part of the theory since ancient times in some sense. So here I've taken, let's say, the sphere. That is O pi. Pi is a representation of SO3. And we're thinking about how that representation decomposes when we just have the subgroup SO2 fixing the z-axis act. So you might know this decomposes into weight spaces indexed by weights between negative t and positive t. And so that's reflected in the fact that the sphere decomposes into these kind of vertical equatorial strips of total volume 1 by Archimedes, if you'd like, that I've denoted here by O pi sigma. So these are the pre-images under the projection map onto the z-coordinate of orbits for O sigma, which in this case are just points, and then we intersect them with O pi, which in this case is just a sphere. And the same picture for PGL2R, or if you'd like SO12, is indicated here. So you get a family of hyperbolas obtained by taking an x-coordinate slice of this hyperboloid. And I mean, one thing you might notice is that in these two pictures, all of the fibers look kind of similar to each other, except when you come near the pole, north or south pole of the sphere, or when you come near this kind of pinch point on the hyperboloid. And at those 2 points, the fiber degenerates, in this case, just to a point, and in this case, it degenerates into kind of a point and the complement of the point, which will be like the complement of the axes in R2. So the orbit structure and also the topology kind of degenerate. But away from that, everything looks kind of nice. So this turns out to be a completely general feature for all of the groups that we've indicated, all of these strong Gelfand pairs, where there's kind of a generic locus that we'll call the stable locus because it's GIT stable, where everything behaves very nicely. All of the fibers will actually be torsors for the action of the smaller group. And then there's some kind of more singular locus, some non-stable locus, if you'd like, where things behave badly. And also, if you're from analytic number theory, you know that there's this phenomenon called conductor dropping, where the analytic conductor of an L function becomes smaller than it typically would, and that corresponds exactly in this picture to where these kind of fibers degenerate. Okay, so one thing we prove in our paper is that under some assumptions, and some assumptions more or less exactly means staying away from the bad cases in these examples. So staying away from the poles of the sphere or the pinch point in this hyperboloid. We proved that the projection norms of the localized vectors, so think of the projection norm of a vector associated to a triangle in this picture, are given exactly by intersecting that triangle, or more generally that partition element, with one of these fibers of the projection map, and then computing the volume. So it's an H torsor, so volume kind of makes sense. So in this picture, all you should think is that, okay, you take a triangle here, and you look at how much time the equator spends in that triangle. So you sample a point from the equator uniformly, figure out the probability that it lies in a triangle like this, and then that'll be your projection norm. So it's something you can kind of visualize and think about very easily. But it lets you do a couple things. I mean, on the one hand, it lets you compute projection norms, and on the other hand, let's say you care about for some particular fiber here, maybe the equator itself, maybe some other one, maybe you want to write down a vector that has a large projection norm along that fiber. Well, you just choose a triangle that kind of sits on that equatorial strip, and then this formula tells you that you get the volume out. So it gives a very, very simple pictorial way to think about the special functions analysis that goes into restrictions. Okay, and yeah, I guess that concludes the kind of general representation theoretic part of my talk. And what I'll next do is I'll give a very quick primer on L functions. If you haven't heard of L functions, I mean, in fact, the main result of our paper, you can stay completely free of the language of L functions. It's all just about period integrals of eigenfunctions and homogeneous spaces. But somehow all the motivation comes from the theory of L functions. So it's an important part of the story, but not an integral part of the mathematics. But okay, before that, are there any questions just on this kind of general part? All right, if not, great. Let's give a quick primer on L functions. So I guess the story starts with the Riemann zeta function, which you can see pictured here, which you can define as a Dirichlet series involving the natural numbers or as a product involving the prime numbers. And this identity makes it important for the study of prime numbers, and it has a long history going back to some of the mathematicians you see here. And in particular, it's of interest in understanding how the primes distribute themselves. So you can count the primes up to some bound, and people classically notice that this count behaved like a simple function. So here's the count, and you can imagine that if you zoom out this picture far enough, you see some limit shape appear. And so that's called the prime number theorem. It was conjectured maybe a century earlier by Legendre and Gauss, and it was finally proved by the authors you see here. And kind of a key step in the proof was to control the zeros of the zeta function. So showing that they only occur to the left of the one line was kind of one of the main steps. And people conjecture stronger properties. So there's a conjecture called the Riemann hypothesis that says that all the zeros actually occur on the half line. And there's a consequence of the Riemann hypothesis called the Lindelof hypothesis that predicts that when the Riemann zeta function isn't busy vanishing on this critical line, so it vanishes, of course, at the 0 as you indicate here, you'll notice that the vertical extent of this graph is quite smaller than the horizontal extent. It only goes up to about 3.5 when you go out to t to be about 50. So the conjecture is that this is a general phenomenon that, in fact, the zeta function grows slower than any positive power of t as you let the argument go to infinity. So these are both kind of wide open questions, but you can ask for approximate versions of them. So one of them is called subconvexity. And so it concerns what's called the growth exponent, for instance, of the zeta function, which is the smallest number e for a given real argument sigma, such that you can bound the growth of the zeta function by the eth power of the imaginary part of the argument as that part of the argument goes off to infinity. So what's indicated here in blue is what's called the trivial bound for the growth exponent, called the convexity bound. So it comes from the fact that we understand everything to the right of the one line because we have a convergent Euler product, and we know how to relate arguments at s and 1 minus s using the functional equation. So all the mystery is about what happens in between these two things, and there's kind of all we have at kind of first glance is a general principle from complex analysis that says that in a picture like this, under some mild assumptions, we can interpolate bounds. So the interpolation from here to here gives the blue line. That's kind of the trivial upper bound for the growth. The green line is what you get by interpolating the Lindelof hypothesis, which predicts that it doesn't grow at all on the half line. And the red line is what's called subconvexity. So anytime you can prove that it grows slower than trivial, slower than convexity in the critical strip, so for example at the 0.1/2, you can interpolate this to a non-trivial bound everywhere. And so for the zeta function, this is an old theorem of Hermann Weyl, who introduced the method, Hardy and Littlewood, who applied the method, and then Landau, who wrote the paper, and also in a more general setting, that in fact the zeta function grows a bit slower than expected. The amount that it grows slower was exactly to scale on the previous slide. And improving upon that exponent has been an active area of research, so the record is due to Bourgain from a few years ago, improving on this 1/6 bound by a little bit more. And there are tens of authors who have kind of improved in between there. So rather than trying to improve that exponent, you can ask to prove bounds for more general classes of zeta-like functions, and those are known as L functions. They all have a shape kind of like this, which looks roughly like the zeta function, but you're allowed to insert some complex numbers as factors of appearing in the denominators. So one example is the zeta function's nth power itself, which is just what you get by taking the alpha to all be 1. But it turns out there are other examples that are interesting in number theory. And not every expression like this is what you call an L function. There are only very specific ones that are constructed in a special way that deserve that name, but they all have this rough shape. So this slide is not intended to be read, but just to give kind of an impressionistic idea of the fact that many people have thought about these things over the centuries. So Dirichlet, Arden, Hasse, Hecke, Hasse-Weil, Langlands. So they've all had one reason or another to introduce some new class of L functions that typically describe some refined property of how the primes distribute, for instance, in arithmetic progressions, or with respect to the splitting behavior in Galois extensions of Q, and beyond. So, Fermat's last theorem this was part of the story there. Okay, anyway, collapsing all of that, there's a class of L functions called standard L functions that are expected to contain all of the above examples. That's the conjecture of Langlands. And these are attached to automorphic forms on GLN in a rather natural way that in particular commutes with natural constructions. So for instance, one rather explicit class of automorphic forms are the Eisenstein series, and those should correspond to these L functions that are likewise explicit, like the nth power of the zeta function. So here's a completely explicit example that ties in with what I think Jack Newton is talking about, or maybe the papers that built on that, nowadays we have a completely explicit example of an automorphic form on GLN arising from this particular Q series that goes back to Ramanujan. So it's a non-trivial theorem that this expression actually defines an L function of degree n plus 1. I just wanted to put down one slide that says, okay, there are explicit examples that one can actually easily write down. Now, why do we care about estimating them? So just in a nutshell, I mean, some people like Hardy, Littlewood, and Weyl and company maybe did it for just the intrinsic interest. But then in the 80s and 90s, there were a whole slew of applications that kind of ended up boiling down to understanding some non-trivial bound for L functions. So if you think of it as a purist, you don't need the applications, but for the history of the subject, this is kind of an important part of the story. So one is this whole story about distributions of points on spheres, so integral points. So if you'd like solutions to the equation n equals a squared plus b squared plus c squared, these all occur on some sphere of some given radius, and you can ask how those points distribute as the radius goes to infinity. So this is, I think, for some number near 2025, for which there exist any solutions. This is how they look, and the question is, do they fill out the whole sphere? Do they uniformly distribute? And what that question boils down to is understanding bounds for a certain class of L functions. So you notice there's a product operation involved in defining the L functions. Okay. Another example is this example of quantum unique ergodicity that asks how eigenfunctions behave as their eigenvalue tends to infinity. And again, for a very particular example, this question boils down to understanding bounds for some L functions, which actually remain open today. So this is kind of one of the main open problems in this subject, to address this question of quantum unique ergodicity from this lens of non-trivial bounds. But we've only been able to do that kind of ineffectively in the work of Lindenstrass and company. And finally, there's a long history of people studying moments, for example, of the zeta function, where there, even to understand what the conjectural truth should be, was an interesting question for a long time. And so we nowadays have like kind of well-developed heuristics that lead to a precise conjecture for how the moments of the zeta function on the critical line should look. And they involve in particular a kind of predictable constant ak that comes from simple arithmetic considerations, and then a more mysterious constant called gk, whose first entries are 1, 2, 42 for the 6th moment, 24,024 for the 8th moment, and so on, where, so I mean, these come from random matrix theory or from the theory of multiple Dirichlet series, and there's an interesting story of how those predictions even came about. This has been rigorously proved only in the first 2 cases, and it's kind of a major open problem to understand even the 6th moment of the zeta function. People have also been interested in understanding moments of L functions of higher degree, not just as kind of a way to maybe gain some insight into this random matrix theory mechanism possibly, but also because one of the main ways we've been able to actually prove estimates for L functions is we first prove an estimate for a moment of an L function involving some family, and then we use that to get an upper bound. So you can imagine that if you can bound this for very large k, that would be a very good way to try to control the size of the zeta function. In fact, it's known that if you can get this for all k, then you get the Lindelof hypothesis. So again, just setting the stage, there's been a lot of interest in understanding moments of the zeta function and L functions. Now, I said that all L functions come from automorphic forms on GLN. Just to add a little bit more detail to the mechanism there. So an automorphic form on GLN to first degree is something like a function on a quotient like this, so some G mod gamma, satisfying some eigenfunction or irreducibility conditions. So you can think of it in terms of differential operators. The ones that commute with everything should have this as an eigenfunction. Also, the Heck operator should have it as an eigenfunction. Or you can think of it in terms of generating irreducible representations. And so in particular, automorphic forms that I'll call V are organized into representations that I'll call pi, which you should think of as kind of the spaces where all of the eigenvalues are the same. These will be typically infinite dimensional representations of GLNR, which acts by translating on the right. And so the way you get L functions from automorphic forms is by taking integrals. So an example that goes back to Riemann, that maybe we've seen in complex analysis classes, is that there's an automorphic form called the theta function, which if you integrate it, gives out up to some multiple that I'll call a special function. In this case, it's just the gamma function. It gives the zeta function. So quite a bit more generally than that, we have many examples of ways to produce L functions by integrating automorphic forms. And generalizing that last example to higher degree is the work of Jacquet, Piatycki, Shapiro, and Shalaika, who showed that if you take, so there's a bit of notation here. So I'm going to write pi for a representation on the bigger group. sigma for a representation on the smaller group, and then we'll have automorphic forms v and u, which are vectors in those representations. If you integrate the restriction of the automorphic form on the bigger group to the smaller group against the automorphic form on the smaller group, this will again spit out some L function obtained by multiplying the representations times some special function. So in the setting of the previous slide, this L function was just the zeta function. The automorphic form on the bigger group was the theta function. The automorphic form on the smaller group was the absolute value to the s, and the special function was just the gamma function evaluated at s. So, and there are similar examples either expected or conjectured for any strong Gelfand pair. So replacing GL with SO or U in this picture. So okay, now what do we actually do in the paper that was cited yesterday? So here's our main result in a nutshell. So we take G and H to be one of these strong Gelfand pairs, so something like GLN plus 1 and GLN. And we take some discrete co-compact subgroups that I'm calling gamma and gamma H inside these groups. And we'll fix a representation occurring in L2 of the bigger quotient. And we'll also fix some kind of collection of parameters for the smaller quotient. So this is just, think of this as like some nice compact ball in parameter space. And then we'll rescale that collection of parameters. And we'll look at all of the representations occurring in the smaller quotient whose parameter lies in the rescaled ball. So a trivial example would be like we saw the moments of the zeta function. So those you can think of as like taking the unit interval in the real line, -1 to 1, rescaling it by t, and then looking at all the real numbers that occur in that rescaling, so between -t and +t. So we're going to consider a moment like that, but replacing the one-dimensional line with the space of parameters for irreducible representations on GLN. So think in terms of the infinitesimal character, if you know what that means. So then what we do is we study the average behavior of the L function relevant for this setting, on average as sigma varies, and we prove an asymptotic formula that gives the expected constant in this setting, where expected constant means what comes from random matrix theory heuristics. And so this was the first time anyone had done anything like this, where I guess the number n here is maybe bigger than 2. So that was one source of interest. The other was that, I mean, if you compare the family size here to the convexity bound of the L function, the two are kind of right at the threshold, meaning any improvement on this asymptotic where you can shrink the rescaled ball by a little bit would lead to a subconvex bound. But I mean, also to a large extent, we just wanted to develop analysis of automorphic forms in higher degree. And imagine I got just a couple minutes left, so okay. So just to give some kind of idea of like how the proof went, because it'll just combine in a kind of direct way two of the things we've emphasized in the talk. So on the one hand, we mentioned microlocal irreducibility, and on the other hand, we mentioned this asymptotic formula for norms of projections. So in the setting above, if we apply Parseval for L2 of the smaller quotient, which means we sum over all sigma here, and also over all u, it turns out that the special functions are defined in such a way that what we get is, well, on the one hand, the integral of the restriction of v squared, and on the other hand, okay, well, of course, we'll get the squares of the L functions, but then when we take the special functions and we average their squares over vectors in the smaller group, we just get the projection norms. So that's what I meant earlier when I said that these projection norms were kind of highly relevant for studying these special functions. So now, of course, we know what these projection norms look like. I mean, if we're given a nice compact set in the cogent orbit and we define brackets E to be the corresponding average of vectors, then that average of projection norms is just the volume. That was what our kind of main theorem from that section said. And on the other hand, we have some, okay, average of vectors that we can try to integrate over a quotient and understand to determine what the moment asymptotic should be. And we do that using, well, microlocal irreducibility, which says that each of these v taus will independently in the limit as tau goes to infinity have invariance under the centralizer of the limit parameter for the tau. And there's a nice feature, which is that if you take a fixed representation and you kind of zoom out the frequency scale that you look at it at, that'll have the effect of zooming out the picture of the coadjuvant orbit, which makes the whole orbit collapse to the nil cone. And points on the nil cone, their centralizers will be unipotent, which means we're in a good position to apply Ratner theory to deduce equidistribution. So okay, that's a long argument in a nutshell, but that's kind of the basic idea of where it comes from. There's also a little thickening argument that lets us pass from weak convergence to convergence of an integral over a subset H, but okay. That's, I think, enough for a first overview. So I'll end with this quick summary slide here. And I haven't mentioned that there actually have been many works that have kind of developed this stuff further in the remaining years and maybe in the future too. So thank you.
Any questions or comments?
Is able to give estimate with a single sigma other than the average?
So your question, is it possible to give an estimate for a single sigma on average?
Other than this average or some sigmas in the field?
I'm not sure I understand the question. Can we give an estimate for a single sigma on average over pi, maybe? Or
the average of the L function, L
yeah.
pi times sigma, and the sigma runs for some certain sets. Yeah.
Yeah.
Can we remove the average and do the same estimate for just one sigma here?
No, I mean, it wouldn't be true because we know that these things vary quite a bit individually. Yes, so we don't, I mean, we expect each of these to individually be like fundamental constants of nature that admit no relation to anything else or to each other. So kind of all that makes sense is to average them or to try to understand how big they are. And this gives some understanding of how big they are.
Thank you.
Yep, thank you.
I imagine you don't get any effective. Okay.
That's a good question because, of course, at the time that we proved this result, all of the known versions of Ratner theory in the generality we required it, which is for like regular nilpotent elements, centralizers for GL3 and higher, were ineffective. But nowadays, people are kind of slowly making these things effective. So, you know, for GL3, this is maybe a theorem. So Amir's here. So I mean, it's Lindenstrass, Mohammadi, Jiren Wang, and then Lei Fang. Lei Yang. Yeah. Okay. Yep. So yeah, many people are working to, and maybe others, maybe their students are nowadays working to effectivize these things. And so there's hope that in the complete generality that we consider here, that one will eventually have effective versions of Ratner, and hence these results can be made effective.
Yeah. I wanted to ask, is it correct, like there's a Duke's theorem, like equidistribution of closed geodesics?
Yeah.
Is this a special case of this general theory?
Yeah, I mean, that is kind of an analog of this, where you change the splitting behavior. You change from SO2 to SO11.
Right.
And then you get the geodesic theorem you mentioned.
I see.
Yeah.
When you mentioned the project, when you found the orbit of sigma, it's pre-image in orbit of pi.
Yeah.
You mentioned that if the projectile have a singular point, then this is the correspondence to the contact dropping case.
Yeah.
Can you explain more?
Sure. Well, okay. Why does it happen? Let's just stare at the picture first. So if pi has parameter t, then the points, okay, I mean, really it has parameters t and negative t, if you know how parameters are defined. And then the kind of vertical coordinates where it drops are exactly, well, t and negative t, which and if you know the formula for the conductor is you take all of the pairwise sums of parameters from the two groups and you multiply those together. So the question is, when does let's say S is the parameter for the smaller group. When does S plus T times S minus T have smaller size than it normally would? Well, that's clearly if and only if you're at one of the two poles here. And then, I mean, indeed, in our paper, you know, a good bit of space is devoted to studying this problem in just like algebraic generality, where we show that the feature you see in this example is completely general. Yeah. Did I answer your question at all, or? I mean, okay, I can't give a nutshell answer because, I mean, okay, so we proved that GIT stability can be characterized by a condition in terms of matrices, for example, 10 by 10 matrices having the feature that they have an eigenvalue in common with their upper left 9 by 9 block. And so you can imagine thinking about that condition in terms of like group actions kind of geometrically. And on the other hand, you can think of a spectral interpretation of that characterization as just saying that, you know, two of the eigenvalues match up. And so that's where you get the link from like the conductor to kind of the geometric properties of the picture. But yeah, I don't think I can do better than that in just a quick response. Yeah.
Thank you.
Yep.
If there's no question, let's thank the speaker again.
Thank you. All right, yeah.
You are up on the global period, like you are value